Okay, welcome back. Today we're doing something a bit different. We're gonna do a beam deflection. So we're gonna start with our beam. Sketch on the front plane, and it's going to be a rectangular beam. And we can do, I don't know, we're gonna do the calculation also. So let's do like 60 by 40. And we're gonna go to our thing here. If you don't know what this is, it's okay, but these are the calculations for deflection. So we're gonna start with area. You can see here B and H, and we had 40 and 60. So now we have our I, which is the moment of inertia around this axis, for bending, which is the axis we're gonna bend around. And then so now let's continue with this. We have our cross section, we're gonna extrude it. We're gonna say we have a 400 millimeter beam around the mid plane. Cool. Now, first thing, we define material. Let's say, doesn't really matter. Let's take something. Stainless steel, is it? Let's put this in megapascal. This is 190,000 megapascal. This I need here for E, 190,000. So that I can have. If you don't know how this equation is derived, that's fine. But you should know how to use it, where for this kind of fixture, you have the maximum deflection here when the force is applied at the edge. You have the X, you have the deflection, you have the angle. If you don't know what this whole thing is, it's fine, but this is an equation and you are able to use it. Now, we have a 400 millimeter long beam. We're going to use 50,000 newtons or 50 kilonewtons, and this we have taken from before. So this is ready to be simulated upon. So this is a super simple simulation, and the reason we do simple simulations, you wait before that. If you don't have your simulation pre-activated, you can go here on the command manager and click this, or you can go to add-ins and click this, and you can also put it on the startup. But as you can see, it takes 10 seconds. Like 10 seconds of the startup of SolidWorks is this. So, you know, it's pretty heavy. Anyway, you go to simulation, you click new study, you choose what you want to do. We will probably in the future do thermal for sure, buckling, why not, fatigue maybe, frequency, yeah, why not, pressure vessel design could be interesting. And yeah, let's do static, call it Cantilever 1. Cantilever. So you arrive at this window. Welcome. So here you will have all your geometries, all your parts. Later on it will be an assembly and we will want more parts there, and yeah, but that's for later. Now connections, right now we are a single part, so we don't have connections because nothing connects to anything. Fixtures. Here you can define the types of fixtures and how things interact with each other, or how you connect something to the ground, or how you connect something to a part that is not in this simulation. We could probably do a 20 minutes video about each of these types, but for now we're gonna take fixed geometry. We're gonna choose this face. And we're gonna be like, cool. Now forces, we want a force on this edge. And we want it to be in SI, we want it to be 50,000 newtons. And I want it to be in a selected direction, this direction. You can see that the arrows are pointing upwards. Fear not. You can reverse direction and be like 50,000. You can also, instead of force, apply a torque or a moment. And you can do a remote force, remote load or mass, which is useful for when you're doing like geometries that are hard or complex or weird to simulate as a whole, and you want to just, you don't care what happens in between, but you know that there's something that's far away and it's applying a moment, and you don't want to get like more complex than you should. So we're gonna do gravity, which is 9.81 in the direction of down, and we're gonna mesh here. There's also a whole, like, you can do courses upon courses about meshing, but this tool is it's not very, like, it's not refined. But for this size, like for this length of 400, you have like what is this, 40 elements along the longitudinal line. That's fine. For this, it's all right. Now we get to the pretty colors. Woo! And these simulations take a very short time to do, to perform, and you get some kind of color and stuff and things. And yeah, all right. So let us go here and be like, we got 6.5 millimeters, but to the power of -1. And this says we have 7 millimeters deflection at the end. Now, what gives? Where is the problem? Our young modulus is okay, our length is okay. Here we have 50,000 indeed. So our units should be okay. This, look at that. Didn't divide by 12. Beautiful, beautiful. Look at this. 7.8 millimeters, 7.9. I'm going to forgive SolidWorks for that. That's okay. So what is happening here? First of all, the first thing you get is stress. Now, I will ignore this because this is obviously because I chose one small line to apply the force onto, which is not realistic. So I ignore this completely. You can say that it's wrong, but I think it's correct. Now, there's a thing called neutral axis when diagnosing a beam or when analyzing a beam. It doesn't matter if it's simply supported or whatever. You have this axis that when you deflect, there's one axis, usually in the middle, that doesn't deform. It's called neutral because it has zero deformation. Zero deformation? No, zero stress. Like when you do this, when you apply this force, can I have this thing here where? Yes, the dildo. What is this number of frames? This is all right. So basically, you can see it slowly as you push down on the beam. Stresses begin to form. Now, because we are deflecting here towards down, you have a tension anywhere above the neutral axis, and you have compression anywhere below the neutral axis. Now remember, the neutral axis is like, there's nothing that tells you this is the neutral axis. It's a theoretical. So you have stresses developing here that are like, look at this. SolidWorks tells you that you are yielding at this, for this stress you are yielding, meaning this force is way too much for this beam design. So like if we go here and take it down a notch and put 5,000 instead of 50,000, and we run it again, we go to our thingy here and update that we changed it by 1 order of magnitude. We also expect to have 1 order of magnitude less. Yeah, that's close enough. This is 0.78 millimeters. This is 0.8. So we have 0.02 error, which is not ideal, but not horrible. You know, 3.6 out of 5. Not horrifying, not ideal. Yeah. So this is how you do your simple beam analysis. Maybe this is why. Yeah, this is why. This is for sure why. For sure. Has to be. Simple. Yeah. All right. The gravity wasn't in the calculation. Of course it wasn't. I added the force and then I'm like, oh, why is this different? But it's still different by less. So yeah, this fixture says this is fixed. This force says there's a force applied in a direction I chose. Meshing, we can probably demonstrate that the mesh doesn't really affect the result. And basically, when you mesh, you want to use the largest mesh you can to get results that don't change when you change the mesh. Did that make sense? Tell me down below if I made sense. It made sense to you. If not, I can explain it again. It's fine. How many elements do we have? Yeah, this is you have 500,000 elements for a simple beam. This is way too much. You should have probably like 1,000 elements here. And would maybe be interesting to see how low we can go on elements and still get the same result. Because like this is calculation time. For this specific simulation, it doesn't really matter because it's very quick. 0.8 millimeters. Okay, so we actually got more deflection. Let's see what happens when we go 7.96. All right, so we got closer, and this is because our mesh is really big, as in it's not, the resolution is not very high. And let's create a new mesh and be like, instead of 40 we go 20. But you see how much faster the calculation takes compared to 500,000 elements. And this is 7.94 e to the 7 and 7.94, so 0.79, same result as previous one. And let's go and do another one. Let's take it down to 10. We're halving it each time, and runtime is very short, 7.97. all right, so it changed the result a bit. Still very minute changes, as I would expect, I would say. Let's run it again. This one should take a bit longer. Yeah, 50,000 is like way too much. Placement 7.98. So very little variation in the way of our result. And yet, if this wait, 7.9. Okay, if this simulation was like something with 10 parts that have nonlinear contacts and friction and bolt connectors and bearings, which you will hopefully, if that interests you, do at some point, runtime is very important, because you can sit there 30 minutes and this thing is hogging your computer, and you're like, me work, I want to work, and each time you set up a simulation or you make a mistake or something, it's like 20 minutes of you sacrificing your time. So you want to be very sure of your boundary conditions, of your connections, and all of that thing, all of those things. And now let's make the floopy. Make it really fast. 50 frames. Ooh. So yeah, most important thing when you simulate is to check your result. I've seen on YouTube simulations where someone tried to simulate a femur bone, the femoral bone, and he got 4 meters deflection, and he was like, yeah, deflection is 4 meters. Well done. Hope you enjoyed my tutorial. Goodbye. And it's like, huh? 4 meters deflection on a bone that's less than a meter long? Are you insane? And yeah, it's super easy to get pretty colors and impress your staff, who are probably boomers and never, like, these tools are way beyond what they could imagine for students. But super important to check yourself like once, twice, 3 times, as much as it takes, because if you trust this software too much, you're gonna lose your edge, and it's going to be very embarrassing. Another thing you should know is this thing. You can click here and be like, don't show me the deformed results, show me the deformed results. You can also go here and press edit definition and be like, no, I don't want the deformation to be 50 times enhanced so that someone can say, oh yeah, it's very. You can be like true scale if your displacement is big enough. In this case, you can see now on the true scale, it's very tiny. You can see that the arrow is where it started, so you have this thing. Cool. Or if you want to like not go insane, but also where is it? And just a bit. So instead of 50, like I would say, let's go times 10. Like, okay, we understand. That's cool. And yeah, that's the first simulation episode I have. I will do more in the future. It's so the geometries take some time to come up with, and also like analyze analytically before, and it takes some time to get this going. So it will really help me if you like, subscribe, send it to your mates, your friends, your whoever might be able to get some use out of it. And see you next time.